Morning, guys. So over the last two classes, we were looking at projectile motion. Projectile motion is studying the two-dimensional kinematics as objects get thrown through the air. We started off with a meatball style question, which is a car driving off a cliff. It was just purely horizontal velocity. We could calculate things like how long until it hits the bottom, how far away the range from the base of the cliff do I land. Yesterday, we started switching over to a football question, which I'm going to practice with you here. For a football question, let's actually just go right into it. So it just says warm up here. Sometimes you do need to just draw a picture from a word problem. So just give you some practice here. Football is kicked from ground level at 35 meters per second. So that's the speed that I launched it at. And it is at, let's make it 60 degrees above the horizontal. Right. So if you can translate that into a picture, right? We can break up our x and y here. A couple things I want you to just try calculating here. I want you to calculate the total hang time. So calculate the total time that's actually in the air, so total flight time. So you notice I'm not interested in a max height question this time. So calculate the total hang time and the range. So this is the horizontal distance. How far should my friend be standing so that they can catch the football? Horizontal distance. And just sort of slightly different wording of the question here. Instead of dealing with a max height where I sort of know that instant in time, I want you to actually just calculate for me here. Determine the velocity at time of 1.2 seconds. So what I did here is I know this football here is going to go up and come down. There is a moment that this football here is 1.2 seconds haven't been launched. And let's say I was really interested in calculating what is the speed at that particular instant. And you notice what's interesting about that question here is I don't know whether it's still on the way up or it's already hit the peak and come downwards. Our goal in doing this question is try to figure that out. So again, I'd encourage you just to pause the video and try it out for yourself. When you come back, you can take a look at how this is done. I'm going to start off drawing a picture here. So we have our football. You're the kicker, right? So the football starts on ground level. We're going to launch it at a speed of 35 meters per second. Again, the problem with that 35 is unfortunately that's a diagonal. We need to break that diagonal up into the x and y first. Yes, you would have to have accelerated the football to get it up to this 35, but when they actually give you that 35, it's already left your foot, so you can't actually impact it anymore. So from here on out, we can say there's no horizontal acceleration, and therefore whatever speed you have at this point here, that's going to be your speed were it not for gravity. Again, this arrow here is going to pretty much follow a parabola. That arrow, I want to show you, it only really applies at t equals 0, because after at least my foot, gravity is already starting to slow it down, so that way it's going to bring down this total arrow here, coming down this way. So let's just take that diagonal. The diagonal is 35. My angle in this case here is 60 degrees. All you need to do is you're just labeling your adjacent and your opposite here. Well, what's the v initial in the x and what's the v initial in the y? So again, we're starting to break up our columns here. Here's what I know about x. Here's what I know about y. You should be able to see that the v initial, or actually just velocity in x, that velocity doesn't change. It's going to be 35 cosine of 60. The v initial in the y direction is going to be 35 sine of 60. So let's punch our way through here. 35 cos 60 gives you 17.5. And then 35 sine 60 gives you 30.3. So essentially what I'm doing here is, I know they gave it to me conveniently sort of together. It's a diagonal, it's 35, but that 35 turned out to be really hard to do in terms of my functions. So what I did is I broke it up. Instead of dealing with 35 at 60 degrees, I'm just going to think, oh, you kicked it forwards, 17.5, and you kicked it upwards, 30.3. Let's see where I'm going to be blindfold on, blindfold off in this question here. This time, I want the total hang time. So from the start, this is where I start my initial. This is my t equals 0. I'm going to totally skip over the max height this time. And I'm going to set my final. I'm only going to take off my blindfold when it has completely hit the ground. That is the total time it's in the air. That's the total hang time, or the total flight time. So let's list my variables based on that situation here. We know the horizontal acceleration is 0, right? No air resistance. The vertical acceleration is negative 9.8. Gravity doesn't care that you're launching it upwards. Velocity can be up. If acceleration is negative, those two are opposite direction, and therefore this object here slows down to a stop and then starts coming back downwards. In terms of the displacement, this is the nice thing for the hang time. In the y direction, from when I have my blindfold on to when I take my blindfold off, I would say, hey, the football is back on the ground level. So therefore my displacement here is actually 0. Again, you can translate that for yourself. The football is back on the ground level. It's as if you didn't go up or down, right? It's just going to be 0 meters. So in this problem here, it looks like I know more things on the y side. So just like we did yesterday, let's go through our formula. D is equal to v naught t plus 1/2 at squared. So our displacement, I'm no higher or lower than where I started, so that's going to be 0. My initial velocity, I'm not going to use the 35. I'm going to use just the 30.3 because that part there is vertical. I don't know the time, plus 1/2 negative 9.8 times it by t squared. Let's clean this up a bit here. 0 is 30.3t minus 4.9 t squared. Again, you cannot kick the all the numbers over to the other side because I need to keep my t terms on the same side. But we're going to use this fact here for all football style questions when we deal with the hang time. Because we are going to end up equaling 0, let's just do a factoring step. Let's factor a t out of this variable here so that I have t multiplied by what's left over in brackets, 30.3 minus 4.9t. Anytime I have two numbers that are supposed to multiply to give 0, either one of the numbers is 0, so in this case it's just t. T could be 0, yet the football is already on the ground. Or this other binomial here, 30.3 minus 4.9t has to give you 0. Again, we can clean that up a bit here, 4.9t over to the other side, and therefore 30.3 divided by 4.9 gives you a t of 6.2 seconds. So essentially, again, let's ask ourselves the question, when is our football on ground level? Well, it's at ground level at the really beginning. I launched it from ground level, and it comes back to the ground level at 6.2 seconds. So let's draw a picture here. So here's the ground level. At 0 seconds, it's definitely on the ground. So far, what we found is by the time you are 6.2 seconds, you're back on ground level. That is the total flight time. If you wanted to use symmetry, you can say, well, if it's 6.2 all the way there, you could have said, well, this one here is going to actually be 3.1 second. This is just giving you sort of an intuitive sort of guess here. You'll notice in part B of the question, I just randomly gave you a time. I just randomly said, can you tell me the speed when it's 1.2? Well, using the symmetry argument here, you can say, well, 1.2 seconds is only here. It should still be on its way upwards. That's going to be my guess. Even if you didn't have the symmetry of the problem here, you should still find the Vy is still going to be upwards because gravity hasn't had enough time to actually slow you down. But again, what I want to do here is, because this is a two-dimensional problem, I need to find the velocity in 2 dimensions. I need to figure out, well, what's my x at this point? And what's my y at this point? So that I can use Pythagoras and put them back together. The x is always going to be easy. In the x direction here, I had kicked it at 17.5. No matter where you are along this path here, the horizontal is going to be 17.5, 17.5, even final, 17.5. So even at this random time that I gave you in part B, I gave you a time of 1.2 seconds. I know the x direction. Let me just resketch that part there. I know the x direction is at least 17.5. I need to calculate what is my Vy at this exact moment, 1.2 seconds, so that I can do Pythagoras, so that I can put it back together. I can find the hypotenuse and I can find the angle. X and Y are completely independent. You can deal with the equations sort of in separate columns, but whenever you need to put them back together, we just set up a right triangle and I use Pythagoras to put them together. So back on the y side here, so this is part B. What is the y velocity if I have a random time of 1.2 seconds? Initially, my y velocity was this 30.3. I had launched it vertically, 30.3. Gravity is going against me, negative 9.8. They gave me a time of 1.2, so that was given in the question. In this question here, 30.3 minus 9.8 times 1.2. You'll notice this velocity here, 18.5. This velocity that we just calculated, when you're at a time 1.2, the velocity is still positive. So that means I'm still on the way up. I'm not going up as fast as I was before. I was going 30.3. Gravity has had a little bit of time to actually slow you down, but I'm still going up 18.5. Now you know this is 18.5. And now we can just do our Pythagoras again. The V is the hypotenuse, so it's going to be the root of 17.5 squared plus 18.5 squared. And then for the theta, we're going to do the inverse tan opposite over adjacent, so the 18.5 divided by the 17.5. Let's see what we get for this one here. The root of 17.5 squared plus 18.5 squared. This gives me here 25.5 meter per second. Let's compare that to the beginning. At the beginning, it was actually going 35 at some angle there. Gravity has slowed down the vertical part, so now I'm only going 25 in the diagonal. And just comparing the angle here, the inverse tan of 18.5 divided by 17.5 gives me here 47 degrees. Again, this is a side view problem. Don't say north of east. You want to say maybe above the horizontal. It's still on its way upwards. It hasn't hit max height yet, but there we go. That's the velocity at 1.2 seconds. They just chose some random time for you there. Right? What we're going to enter in here is we're going to now apply sort of what we know about the football question and the meatball question to one last setup called a cannonball question. We're going to skip over to our simulation again just to have a quick look, and then we'll come back and we'll do one problem fully worked out. Okay, so we're back on our simulation here. You can access the simulation under the link I give you in the resources section here. But just looking in general here at the projectile motion setups we've done so far, the first 2D problem that we dealt with was a meatball question. Again, we had a car driving off a cliff. They're just going to use a cannon for all of this one here. The cannon is going to accelerate the cannonball or the projectile. It's going to be accelerating it, launching it at a certain speed, whatever speed that I give it. So far here, I'm at 0 degrees. I'm just going to send it out at some horizontal velocity. If we assume that there's no air resistance here, basically it's just going to be like a car driving off a cliff. The wheels are no longer in contact with the cliff at all. It can't speed up or slow down horizontally. Although gravity does have a negative 9.8 acceleration, it is going to gradually bring you downwards. We're going to see this sort of parabola-like shape motion. That was our first setup. For a football style question, what we did is we ended up putting our cannon back on the ground level. So now we actually have the football at the ground level. Now we want to aim it somehow at some degrees. We fired this projectile here at some diagonal. Because this one here at first was a diagonal, I actually need to break down the x and the y before I can deal with my columns. And now, as you might imagine here, my last setup here, which will be a cannonball setup, what we're going to do is we're going to put those two problems together. What if I was actually on height again, let's say back at 10 meters, but instead of launching it horizontally and just getting this sort of the straight on and the half the parabola here, what if I actually, almost like a football, I launch it from this cliff at this direction here. So we're going to do that motion here. We sort of intuitively know what's going to happen, right? It's going to be a parabola-like shape. It's just that we're going to see that for a cannonball style question, the math is just going to be a little bit more challenging. We still will need to take, just like a football question, because I'm launching it at a diagonal, I need to break down the x and y parts. I'm going to need to separate the x and y columns so that I don't accidentally use the x values and the y values in the same equation. Anytime I want to piece the two x and the y directions back together, I need to use Pythagoras. We use trigonometry to find our angles. All that is the same. What I want to do with you here is I want to just actually show you our cannonball is actually a combination of the football and the meatball question. Because if you look at this here, if you pretend the cliff height is my ground level, you'll notice this first part of the motion here is just a football question. I launch it from ground level, I launch at a diagonal, you break up your components. This is going to end up hitting some peak height. Basically, gravity would have removed from you all your vertical part of the velocity. That part there we've done before. That's a football question to the max height. The football question then mirrors that image. It says, well, it's going to be halfway up to max height. It's going to be halfway down to max height here. Football question would sort of be this top part. But you notice because for a cannonball question, we're not completely done with a d of actually 0. This one here actually falls past, right? Even though I started out atop this cliff here, this football here actually falls past my starting cliff level. So what we're going to do instead of worrying about this being a full football question and there's some weird random addition here, we're just going to think of this as a football question at the really beginning, just up to max height. At max height, I'm going to have no y velocity. All my velocity will be in x. The x just continued on going forwards here. If I imagine just a meatball style question here, if I drive off a cliff here horizontally, I will follow down this new parabola here all the way downwards. You'll notice this latter part here is actually just a meatball style question. Now, one caution if you do that though, for a meatball question, we used to be, well, here's the cliff of the height. Here's the height of the cliff here. That's how tall I'm actually launching from. You'll notice because this cannonball here actually launches you a little bit higher, you actually would need to calculate how far up from the cliff level are you from the football question. And now we actually have not only the 10 meters worth of cliff height, you have the 10 meters plus the max height from the football. That's how far I actually fall for the meatball question. So intuitively here at Cannonball, here's those two parts here. I generally find it's a little bit too tedious trying to calculate all the little bits just so that it can matches up nicely. What we're going to do is we're going to set, sure, we can still do a max height question just like a football. It's identical. But what we're going to do is we're going to set initial to be when I launch it. So be it, it's on an angle. So be it, it's on the cliff. And we're going to set the final to be at the really, really bottom. Again, the math is just going to be a little bit harder, but we'll just work through one just in all the detail. So let's have a look together. Okay, so we're back on our OneNote here. Let's try out one of these cannonball style setups. This is about as hard as the projectile motion questions get. It is still two-dimensional kinematics. So here's our cannonball question. Just like we saw in our simulation here, we're actually going to be atop a cliff at the beginning. So I'm going to have a cannon. It's going to be propped up at some angle here. Just like a football question, it's going to be launching your cannonball at a certain speed. Let's say it's 15 meters per second. And let's say I launch this one here currently at 30 degrees. Keep the numbers fairly simple. Intuitively, again, our parabola, again, that speed only applies. The cannonball has already been accelerated through the cannon, right? There was some acceleration at the first, but when they give me this 15, it's as if the cannonball here is free floating here. It's just 15 now, and now it's just going to be flying through the air, eventually hitting the ground below. As you just talked about here, this first part here looks a lot like a football question. It's a football just until the max height. That's what we're going to do in the first part of the question. If you then imagine that the remainder part here, well, if the remainder part here is just a meatball question, I'm actually just traveling horizontally and I'm going to follow this distance. Careful, I'm following the distance of the height and the max height together. This part here is just a meatball question. You could break it down like that and you could solve it in that fashion here. So there's my setup here. I'm going to give you the height of the cliff here. Let's say this cliff here is only 10 meters up. Let's do sort of part A, B, C, so you can actually practice out for yourself here. Part A, let's just deal with a max height question. So max height. This part here is essentially a football question, right? So for max height, what we're going to need to do, because this one here is currently a diagonal, I need to break up that diagonal. So I'm launching it upwards at a 15. The angle is 30 degrees. How much of this is x and how much of this is y? And noting that this is an initial velocity. So our Vx, or our V initial x if you like, 15 cos 30. The other side, V initial y, is 15 sine of 30. Make sure you're in degree mode for all of this. 15 cos 30, this one is 12.99, so let's say 13. 15 sine of 30, this one gives me here 7.5, right? So those are your velocities. Because I've broken up the diagonal, I don't need the 15, I don't need the 30 anymore. I can actually plug into my columns. If I list for myself variables, what I know about x, what I know about y, I know my velocity in the x is 13, and I know my velocity in the y started off at 7.5. So we have those ones there. Acceleration in the x, again, after the cannonball is leaving the cannon, I can't influence anymore. Assuming no air resistance, there is no horizontal acceleration. There is an acceleration for gravity as negative 9.8. If there was an acceleration, you just punch in the a term here, and you'd actually use that value in your formula, so it's not much different. For a max height question, we know one other value. In terms of the vertical here, this object here is going to start climbing all the way to the top until it hits the peak. The peak in the y direction is not going up or down. The final y velocity is actually going to be 0 meters per second. So I actually have that information. So we know more things about the y, so let's just calculate it from there. Let's go v is equal to v naught plus at. If at max height, I'm not going up or down. I initially was only going up 7.5. Gravity is an acceleration 9.8. It's going to change my speed by 9.8 for every second. How long would it take gravity? Right? Probably not even a second here. So I'm going to bring the negative 7.5 over. I have negative 9.8. And therefore the time, just to hit the top, 7.5 divided by 9.8 gives me here 0.77 seconds. Right? Time should be positive, right? So from when I launched the football, that's 0 seconds. Within a second, this thing here has already come to a stop. Let's also use our other equation. Because I know the final velocity, I'm sort of leaning towards using those equations. Right? We can use the equation if there's only one unknown in it. Again, at the top, I'm not traveling up or down. I had a 7.5 squared. How far do I actually climb by the time gravity has actually brought me to a stop? So I have a 0. Most common problem in this formula here is people forget that these things here are squared, so make sure you don't miss those ones there. Minus 19.6d. I'm going to drag the 19.6d over. This gives me 56.25. And I'm going to divide the 19.6. And this gives me here 2.86, so let's just say 2.9 meters. Right? That is basically a football question, right? If I had launched it from ground level, here, you're going to be 2.9 higher than where you started in 0.77 seconds. So again, just back to my diagram here. I calculated just up to the max height. Our time is our 0.77 seconds, and our distance was 2.9 meters. Notice that distance is assuming we were at ground level. It's telling you that this distance here is 2.9 meters. So if you really wanted to break it up into a meatball question, I want you to picture our new cliff is actually 10 plus 2.9. Our new cliff is actually 12.9, and gravity actually has to pull you all 12.9 downwards, not just the 10 meters of the cliff. Again, it's a little bit tedious trying to do it that way here, even though the math is a little bit more challenging. We'll see in a second here. What I'm going to do is I'm going to reset my initial and final. For the max height question, I have my blindfold on here. I took off my blindfold at max height. That's why I set VF to be 0. This time, I'm just going to reset. Initial is still going to be launching. I know a lot about that information here. And what I'm going to set my final to be at the really, really bottom, right? When it finally hits the bottom, 10 meters lower. So in that case there, let's again label some of these variables here. So B, let's do the total hang time or the total flight time. Lots of the numbers haven't changed, right? So X and we have Y. In terms of the X direction here, because my initial is still my cannonball launching, my X is still going to be 13. My Y is still going to be 7.5. So X is going to be 13. My Y is going to be 7.5. That was just upon breaking up the diagonal. The accelerations are still the same. Assume no air resistance for the X direction. There's no air resistance for the Y as well, but for Y, we definitely know gravity is the thing that's causing it. What goes up has to come down. This time, I don't know the VF, because if I set the final to be here, in fact, the VF is going to be the fastest moving speed down here, right? It's going to be something that's non-zero. It's going to be the biggest, the fastest this football ever moves. So I don't know the VF anymore. However, I do know the D. The displacement in the Y direction from when I had my blindfold on, I didn't realize it went upwards and then came downwards. When you tell me, yep, done, I take off my blindfold, I realize, wait a second, we're 10 meters lower than where we started. Sure enough, you had gone up 2.9, you went down a total of 12.9, but in total compared to my start, we're only 10 meters lower. So I'm actually going to punch in here, the D is actually in the vertical, negative 10 meters. And by setting the initial at the launch point, by setting the final afterwards, I didn't need to deal with the max height at all. Again, formula-wise here is exactly the same. D is equal to V naught T plus 1/2 AT squared. Let's see if we can find T, and then everything else falls apart. It's just that the math is a little bit harder. We'll see in a second why. So let's just punch our way through. The D, I end up 10 meters. Let me write this down for you. We end up 10 meters below our start point, our launch point, even though this one realistically went up and then went down. Right? That's the whole sort of benefit of doing it with vectors here. I don't really care what happens in between, right? I just care the overall displacement, the overall. So sure, you went up 2.9, but you fell down 12.9. In total, it's like you have just went down 10, right? So that's a negative 10 there. The initial velocity here is going to be 7.5. That's positive. I don't know the time. Plus 1/2, a negative 9.8 for acceleration, t squared. This time, unlike a meatball question, this was 0. It killed off this t term, so I can just square root. This is not a football question, because for a football question, for the total hang time, this was 0. So I can factor it. I can just do a binomial. This time, I'm out of luck. I actually do have a t squared term. I have a t term. I have one that doesn't have a t term. This should look like a quadratic to you. So therefore, you can just solve your way through this quadratic. So let me just clean this up here. I have negative 10 is equal to 7.5t minus 4.9t squared. I'm going to bring all my terms over to one side. It really doesn't matter which. Let's drag it over to the left, let's say. 4.9t squared minus 7.5t minus 10 is equal to 0. Uh-oh, we're trying to solve for t. Well, perfect. This is my exact formula for a quadratic equation. All we practice on the sort of first couple classes here is if you can identify for me the constants. Well, A is 4.9, B is actually negative 7.5, C is a negative 10. My quadratic formula, mathematically, it was a little bit harder, but it will give me the time that I need. So let's just go to our formula sheet here. For the quadratic formula, we're actually looking for t. It's negative b. Even though I know what a, b, c are, I'd still copy out the equation. So just to make sure I do all the right math to those numbers. And here we go. We're going to take the negative of b. B itself was negative 7.5, so negative of negative. There's a plus minus. I'm going to take a negative 7.5. Make sure that part there is squared. Don't type that into your calculator, negative 7.5 squared. Your calculator would do the 7.5 squared and then add the negative afterwards. What we want is, no, the negative times the negative, so that actually becomes positive. We're going to minus 4 times a, which is 4.9. C is negative 10. All that's underneath the square root. All over 2 times a, 4.9. So again, there was no shortcut. We couldn't square root. We couldn't do some factoring. Again, sometimes in math class, you try to do like, oh, two numbers I multiply to give a times c and add to give this. Whenever there's decimals, that becomes way too hard. The quadratic formula, however, always works. So let's just go straight to it. 7.5 plus minus. Let's just deal with what's underneath the bracket here. 7.5 squared minus 4 times 4.9 times negative 10. Underneath the square bracket gives me 252.25. I need to take the square root of that, so that gives me here 15.9, give or take, divided by 9.8. At this point here, I'm ready to separate the plus and minus. So one side takes the plus root, takes the plus answer. The other side takes the negative answer. So let's just punch our way through. 7.5 add 5.9. Make sure you do that part first, divided by 9.8. And then 7.5 minus 15.9 divided by 9.8. So let's figure out the two mathematical times that this ends up working out. 7.5 plus 15.9 divided by 9.8 gives me here 2.4 seconds. And on the other side here, 7.5 minus 15.9 divided by 9.8 gives you here t is negative 0.86 seconds. There are mathematically two solutions that you are 10 meters lower than where you start. Because time has to be positive, I'm going to reject the negative because this is not a physical solution. Our physical solution, the one that's important to me, is the positive time. But let's just think for a second here, why is it giving me two answers? If you think about this cannonball style question, remember all these projectile problems, all of them ended up as a sort of parabola-like shape. So what this is sort of doing here is we have a parabola, right? Here's our equation. All I'm asking you for is when does this parabola hit 0? Or in our question here, it's when does our projectile, when is it 10 meters lower than the ground? So in this case here, here's my parabola. We started off here. That's when I decided to say t equals 0. My clock starts ticking forward. So time of 1 second, time of 2 seconds. Time of 2.4 seconds is when it hits the ground below. That's when we are 10 meters below the ground. Is there another time we're 10 meters below the ground? Definitely not a physical solution. But pretend this parabola here was sort of continued. It was actually going into the negative times here. If I actually launched this as a football from down here, that time there would have actually been negative 0.86 seconds. It would have taken you 0.86 seconds just to climb up to the top there. And that's why we actually have a negative answer. No bearing in this question. It's not important for us. But mathematically, that's why it's giving you those two answers. There are two possible times. One, I'm setting t equals 0 here. Two possible times that this parabola ends up saying my projectile is 10 meters below the ground, and that was the formula that we ended up solving for. Now we actually got the time. The whole other problem falls apart here. I forget what else I asked you here. Let's see if I can calculate the range. So calculating the range here is in the x direction. We just go d is equal to vt. We haven't really used horizontal at all. Horizontal was 13 meters per second. It was 13 all the way through. 13, 13, 13, right? It just kind of keeps going. At the really end, it's still 13. If I travel at 13 meters per second for 2.4 seconds, that's when I can tell you, oh, I've hit the ground. I'm not going forwards anymore. 13 times 2.4 gives you 31.2. That's going to be the range. That's going to be the total distance going this way, 31.2. I'm going to calculate as the last step here, calculating the final velocity, just for kicks here. Again, no matter how vertical this parabola looks like it's getting, because this is a two-dimensional problem, there was no x acceleration. There always is going to be a 13, even the instant that it hits the ground. All you're going to need to do then is you're going to need to calculate here, if gravity had 2.4 seconds, what is the final y velocity? And therefore I can use Pythagoras to put that part together. Again, let me just zoom in there so you can see it a little bit better. The instant before hitting, it's my diagonal, that's my purple. Going forwards here, I'm going 13 meters per second. That number doesn't change. I want you to calculate here Vy. Right, so back in the y column here, what is the final velocity if gravity has had 2.4 seconds to actually speed you up? So initially I was going upwards. Let me just look up my numbers. Initially I was going upwards at 7.5. Gravity does pull with a negative 9.8. Earlier in the max height question, we were just finding the time it takes you to bring you back to 0. This time I know the total time is 2.4. I want to know how much downwards velocity I have immediately before hitting. 7.5 minus 9.8 times 2.4 gives you here negative 16 meters per second. Well, why is it negative? Well, gravity is constantly it slows you down from 7.5 to 0. What goes up has to come down. This part here actually just means downwards. So now we know the V final is actually 16, and therefore we can just find the V here. The V is the hypotenuse, so we're going to go the root of 13 squared plus 16 squared. And we can also find the angle, because this is a vector, we need to have the full direction here. The angle is going to be opposite over the adjacent, so 16 over our 13, and we'll just plug our way through. This is the final velocity here. This time there's no symmetry because we're sort of lower. We actually hit the ground below. We're not still at the same height level. But we now know that the final velocity, the diagonal, is actually 21 meters per second. And my angle is actually inverse tan of 16 over 13. Gives me here about 51 degrees, again, below the horizontal. Okay. So what I wanted to show you in that problem here is it's a very similar setup, right? It's still 2D projectiles separating components x and y. It's just the math was a little bit harder, mainly because of this. When we use this formula here, we had to actually use a quadratic formula. There was no way around it. Fortunately, we've gotten enough practice with quadratic formula here. We know how to solve that root part. So I'm just going to leave you with this question here for you to practice. Not quite a cannonball style here, but you'll see the connection to this. Let's imagine I was playing basketball. So let's imagine I'm just standing here. The hoop is just sitting there, right? What I'm going to do is I'm going to launch this basketball. I'm going to throw it upwards at a diagonal. I'm shooting for the hoop, 50 meters per second. Let's make the angle here. Let's make it 50 degrees. Right, so that's how I'm angling it upwards. The only time I can influence the ball is when it's in my hand. When it actually has this 15 and 50 degrees, it's already left my hand. This object here is just going to sort of fall through a parabola. I'm hoping it swishes. I'm hoping it goes straight through that hoop there. The hoop, I'm going to tell you, this hoop is 3 meters high, so sort of off the ground here. Let's say I do make the shot here. I want to know how far sort of horizontally I am standing from the ground. If you just sort of picture, this is sort of like a reverse of a cannonball. The cannonball would have started out up here and actually shot it. It goes to max height and then falls lower. This is just sort of the reverse of that there. So I want you to find for me here. So part A. Can you calculate? That's going to be the hard part. Calculate the time to reach the hoop or to reach the basket. Okay, that's when you need to use a quadratic formula. Determine or deduce. Determine the range. So how far horizontally am I actually standing from the hoop? If I'm too far away, my parabola here wouldn't have landed in the hoop itself. But seeing as I scored, I want to know how far, the range x. And then C, deduce. I'm just going to try to get you used to different command terms here. Deduce the velocity through the basket. Right, and that velocity here, again, you can probably see it here. This is going to be some diagonal. The x part is going to be unchanged. The x was always going to be the same speed. There's no horizontal acceleration, but you're going to need to calculate the y part and do what we just did there. Use Pythagoras and get the diagonal, get that angle there. All right. So see how you do with that question. There's more practice questions on your worksheet, and we'll pick it up from there. Thanks, guys. Take care.